things we don't know. Putting science in your hands.
On the 12th of August 2013, NASA's Juno spacecraft reached the halfway point on its journey to Jupiter. Since launching back in 2011, it has travelled over 10 times the distance from the Earth to the Sun, and has performed a series of planetary flybys and deep space manoeuvres. On October the 9th of last year, Juno came within 350 miles of the Earth's surface. This is known as a gravity assist or gravitational slingshot. After Juno said its farewells to planet Earth for the final time, it started racing towards the Jovian system for its slated arrival time of 22:29 Eastern Standard Time on the 4th of July 2016, give or take a few minutes. But what has Juno done since launch? Well, the Jovian Explorer has been sent out past the orbit of Mars and performed crucial deep space maneuvers to set itself up for its final flyby of the Earth. In a press release, the Juno mission's project manager Rick Nybacken explained further. On the 9th of October, Juno came within 347 miles, or 559 kilometers, of the Earth. The Earth flyby then gave Juno a kick in the pants, boosting its velocity by over 16,000 miles per hour, over 7 kilometers per second. From there, its next stop Jupiter. It's almost like having a second launch for free. If you're confused, try to think of it this way. If a golfer puts a ball towards the edge of the hole, and the ball doesn't fall into the cup, but instead hits the very edge of the hole and lips out, the ball will shoot off in another direction at a faster speed than it went in. However, it is also worth noting that as well as this extremely predictable increase in speed, the spacecraft also experiences a tiny change in velocity due to something else. But just why do spacecraft that fly by Earth receive this tiny change in acceleration? Well, to put it simply, no one is really quite sure. This is known as the flyby anomaly, and it's something that science doesn't really have an answer for at the moment. Scientists have theorized, and then later dismissed, that this unexpected source of energy might be caused by the atmosphere, by tides, magnetism, or maybe radiation. The possible remaining solutions for this problem include that there might be a halo of dark matter around the Earth, as well as the theory that it is caused by the rotation of the Earth itself. In 2005, the European Space Agency's Rosetta spacecraft made the first of its 3 Earth flybys planned for the mission. The first of these flybys resulted in a predicted increase in velocity of 4 kilometers per second. However, the mission team also found a really small change in velocity of 1.82 millimeters per second. That's 2 million times smaller than the main boost, as a result of the anomaly. This is why mission planners can safely ignore it, but scientists who have been trying to figure out the exact cause of this puzzle will be eagerly awaiting Juno's flyby data to see how much of an increase in velocity it will receive from the Earth, and watching closely for any unexpected variations that might be due to the flyby anomaly. It seems Juno might be able to solve some tough questions even before it gets to Jupiter. When Juno arrives at Jupiter in 2016, it will orbit the gaseous planet for around a year, completing 33 orbits around the planet's poles and using onboard scientific equipment to probe beneath the planet's obscuring yet beautiful clouds. The main goals of the Juno mission are to find out how much water is in Jupiter's atmosphere, which helps determine which planet formation theory is correct, or if new theories are needed. To look deep into Jupiter's atmosphere to measure its composition, temperature, cloud motions, and other properties. To map Jupiter's magnetic and gravity fields, revealing the planet's deep structure. And to explore and study Jupiter's magnetosphere near the planet's poles, especially the auroras, the northern and southern lights, providing new insights about how the planet's enormous magnetic force field affects its atmosphere. One of the main mission objectives is to discover how a giant planet like Jupiter came into being and how it evolved. This cloudy world is a primary example of a giant planet and can give us clues as to how other giant gas planets, known as hot Jupiters, which we have discovered orbiting other stars, may have formed. Juno will accomplish this by studying the planet's cloudy atmosphere and its overall composition. One such scientific instrument aboard Juno is its magnetometer. This sensor, located on the spacecraft's magnetometer boom, will accurately map the magnetic field of Jupiter and try to understand how it is generated deep within the planet's core. In 2017, after completing its primary mission objectives and 33 orbits around Jupiter, Juno will perform a series of de-orbit burns to take the spacecraft out of Jovian orbit and into a destructive re-entry in Jupiter's upper atmosphere. But first, on the 9th of October 2013, Juno returned to within 350 miles of the Earth to say one last goodbye to the planet Earth, before heading to Jupiter to try and unlock some of the secrets of our solar system's biggest planet.